Create optical lighting and illumination and laser systems with OpticStudio, the industry-leading optical design software from Zemax.
Thank you very much for joining me today, and welcome to another Zemax webinar. The topic of the webinar today is an OpticStudio demonstration. My name is Kristen Norton, and I will be your host. All right, so here's an outline of the topics that we will be covering today during this demonstration. So I'll start with just a quick introduction about myself, and then we will jump right into OpticStudio and start with a microscope sample file. Then we will analyze the initial performance, and then we'll optimize the system using a variety of our optimization tools. After that, we will lock down the design so that we can run a few different kinds of tolerance analyses, and then we will convert the file to non-sequential mode for stray light analysis. So as I mentioned in the very beginning, my name is Kristen Norton. I'm the OpticStudio product manager. Before being the product manager, I was a senior optical engineer here at Zemax, and prior to that, I was a laser and optics engineer in the hardware world. My background is in physics and applied physics. Without further ado, let's jump right into it. This slide shows the requirements that we'll be using when optimizing the OpticStudio file. The screenshot shown here is the starting file, and as you can see, there's a lot of work that needs to be done. But we are going to increase that first air spacing that you're seeing. That's the distance from the object plane to the first lens, and that needs to be 170 millimeters. We're also going to be setting up the system for an object that is 16 millimeters in diameter. And we want to use this with visible light, so we'll need to make sure that we add wavelengths representing that spectrum. We'll also be optimizing the system with a semi-diameter margin of 0.01 inches. All right, so that will automatically extend the semi-diameter of all of our surfaces, so we have a little bit of margin. And we'll also be designing for a magnification of 0.02. We know it's negative in this case because the image will be flipped upside down. Okay, so I'll switch to OpticStudio. Here I have the sample design file open. This almost matches a design file from ZBase, although we've modified it a little bit. Okay, so here in the lens data editor, you can see that my starting spacing between the object and the first surface is 10, but this needs to be changed to 170 millimeters. I know that this is in millimeters because if I look in the System Explorer, over in the units section, my units are in millimeters here. Let's see, so I also need to change the field settings, wavelength settings, and also the system aperture settings because I need to define a bit of system aperture margin. Okay, so let's start here with aperture. By default, this is the first section in the System Explorer, although note that you can drag it around and reorganize this to your liking. So we're going to set that fixed clear semi-diameter margin in millimeters here, and converting 0.01 inches to millimeters, we get 0.254. You can see the automatic clear semi-diameter here in my lens data editor automatically increased a little bit. And next, I'll set the fields. Because my object surface is a finite distance away from the first surface in my lens data editor, I can use the field type definition of object height. Now, because I need my full object diameter to be 16 millimeters, I can set the maximum field or half field to be 8 millimeters. And I'll use the equal area fields button here to automatically calculate an intermediate field point. And now we have 3 active fields, all with a weight of 1. So I'll close that. And now I need to change the wavelengths here. I'm going to double click to open up the wavelength data editor. And there's only one default wavelength turned on. So I'm going to use the preset wavelengths here for the F, D, and C lines representing the visible spectrum. And you do need to click Select Preset to push this selection in the drop-down menu up into your wavelength data editor here. Okay, now let's look at what we have in the 3D layout. Here, zooming out, you can see this looks pretty bad. Indeed, we're nowhere near focus, but we can run a quick adjustment to bring this image plane in a little bit and just adjust this last air thickness. That's up in the Optimize tab. It's the Quick Focus tool. So we're going to do a really quick adjustment of that last air spacing to find a plane with a smaller spot size. Click OK. All right, and that looks much more reasonable. You'll notice that the settings here have the rays colored by field number, but I did add additional wavelengths, and I can change the rays to be colored by the wavelength, in which case OpticStudio will choose a color that is closest to the true wavelength color you've selected. So it's really only applicable in the visible spectrum. Otherwise, the rays will be drawn black. Or you can select wave number, which just assigns a unique color to each of the wavelengths that you've defined. So here I'll select wavelength. And if we zoom in on the image plane, we can start to see some wavelength separation here. You can see the blue, orange, and red rays are separated based on their wavelength. Okay, let's open up some other analyses and see what we have right now. Let's start with the standard spot diagram. Okay, I'm going to expand the settings and turn on Show Airy Disk. So here you can see the system is far from diffraction limited. The airy disk is really small right here in the middle. You can also see the size of the airy radius here in the text section compared to the size of the RMS and geometric radii for each of your field positions. Okay, let's see. We can also open up some other analyses like the ray aberration fan. This is a good analysis to use if you are not diffraction limited. And here, just looking at the shape of the aberration, ray aberration fan for all three field positions, we can see a cubic shape, which indicates spherical aberration, although the tails are brought in a bit due to the intentional focus here. Okay, so that's being used to compensate for spherical aberration. You will notice, though, that all three wavelengths lie very close to each other for each of these fans, which indicates our starting system actually has pretty good color correction. You can look at aberration of the chief ray passing through the center of the pupil versus the marginal ray out here to look at axial color and lateral color. So here you can see, at least at this field position, our chief ray for all three wavelengths all lies at the same point, but then you can see some color separation out here of the marginal ray, which would cause a wavelength-dependent focus and which would show up as the traditional chromatic aberration. Zooming in on the ray fan for our off-axis field point, you can start to see some separation of the chief rays, which would show up as lateral color or color fringing. Let's look at more of a full field analysis here. Look under the extended scene analysis and open up image simulation. This is using the settings that I had defined previously. So here, let me go in. And so this is a photo that I selected, which if you saw my recent image simulation webinar, we talked about setting this up. So right now what we're looking at are the geometric aberrations as well as distortion. If you want to see the effect of distortion on this as compared to the geometric aberrations, we can set the aberration setting here to none. And you'll see now the image looks pretty crisp, which would indicate that the dominant aberration is spherical and distortion has little contribution. There are a few ways that we can validate this. If we look in the Analyze tab, under aberrations, let's check out the grid distortion. Okay, as we expect, you can see even zooming in on the edges, the blue X's here indicate where the rays really land, whereas the black grid indicates where they would land in a perfect unaberrated system, and we're still very close to ideal. This also is a pretty simple system with spherical surfaces, so we could look at the Siedel diagram to get a good feel for the different aberrations in our system and how each surface contributes. As expected, distortion here is yellow, and there's hardly any of it, whereas spherical aberration in red dominates throughout the entire system. Okay, so we've got a good feel for how our system is performing right now, but let's try to optimize it. So now we're going to move over to the Optimize tab, and let's start with some of the manual adjustment tools. We already looked at the quick focus tool, but now let's try the slider. The slider tool allows you to drag this slider bar to adjust one of the parameters in your system. So let's say I want to look at the surface 6 radius of curvature. Okay. So if I look in the 3D layout, oops, I have to zoom back out. We're going to be changing the curvature of this surface here. So surface, let's say radius, and we're going to do surface 6. I'll also pull up the spot diagram in front so we can watch both of these analyses update. Okay, so I can manually drag this, and you'll see here the spot diagram gets worse. These spots are getting bigger, even though the shape of the surface is not changing that significantly in the layout. Okay, so you can drag it both ways. And actually towards this end now you can see the scale on the spot diagram changed. So this actually has a smaller spot than where we originally started. You also can animate the slider, in which case it will automatically update the windows that you've specified here as it moves this slider along. Now let's say that we wanted to animate multiple parameters at once. So let's say that I could vary all of my radii of curvature. Let's go to the Optimize tab, and I'm going to use the shortcut button to set all radii variable. Now you can see all radii that are not infinity and which do not have a pickup assigned to them now have V's, indicating that they can vary when we run an optimization. It also means that when you open up the Visual Optimizer, it will automatically grab all of the parameters we have set to be variable so that we can manually drag and try adjusting these different parameters. Now let me do that with these windows open so you can see the effect. Okay, so it behaves just like multiple sliders. Similarly, you can choose to animate it and allow all of the different parameters to vary at once. Okay, but both the slider and the visual optimizer are considered manual tools, but OpticStudio has a more sophisticated way to optimize and automatically find the best values for all of these parameters. So let's go to the Optimize tab and now open up the Optimization Wizard. So I'm going to optimize for the smallest spot size. Okay, so I'm changing my criteria to spot radius. I'm not going to explain all of the settings here, but if you do want more information, just click this blue question mark here, and it will open up the help files to this section, and it includes definitions for all of these settings. But I need to change the number of rings here to 4 because later on I'm going to change one of the surfaces and add another degree of freedom, in which case I will need a little bit higher sampling density. Let's see. I'm also going to add some boundary values for my lenses since I am changing the radius of curvature and I want to make sure I have reasonable edge thicknesses in at the center of the lens as well as at the very edge. So let's say the smallest value for the center thickness of my lens could be 0.2 millimeters. And let's say they can't get bigger than 5 millimeters at the center. And then at the edge, it needs to stay thicker than 0.2 millimeters. Okay, then I click OK, and it will automatically build a merit function for me. The first section contains boundary operands that are dictated by the 0.2 millimeter and 5 millimeter values that I entered in. And then a little later down, you'll see the operands that were automatically added for the fields and wavelengths, which I had specified in the very beginning. And these operands will calculate the spot size and work to minimize it. See, the target is 0 for all of them. So this merit function would optimize to get the smallest spot size, but there was one other criteria that I haven't accounted for yet, and that is here, designing for magnification of negative 0.02. I can easily add that in and customize this merit function by inserting in an additional operand. I'll use PMAG, which is the paraxial magnification. Let's just use our middle wavelength 2. That's the default. And my target is going to be negative 0.02. And I'll set that to a weight of 1. Now we can update the merit function to see what value it is now. It's actually very close to this already. Okay. And now I'll run a local automatic optimizer. This local automatic optimizer is automatically varying the values of all of the radii of curvature, which I'd set to be variable. And each iteration of this is attempting to drive the overall value of my merit function to 0. This is called a local automatic optimizer because it automatically stops optimizing when it believes it's found a minimum value. And in this case, it's a local minimum. Okay, so very, very quickly, and let's see, under 2 seconds, in about 1.5 seconds, my merit function was significantly reduced. So let's exit out of this and see how our system has changed. So I'll update the 3D layout. This looks like the shape of the lenses has changed a bit, but overall the system doesn't look like it's changed too drastically, which is also in part because I didn't set any of the thicknesses to be variable. If we update the spot diagram, you can see the scale changed significantly. Now we're down to a 20 micron scale. So my spots have become much better. We see significant improvement. We can also open up the image simulation tool again to see how that improved. Okay, and already you can see it looks much better. So when you have more than a few values set to be variables here, it often helps to run a hammer optimizer as well. The hammer optimizer is very similar to the local automatic optimizer, except that it doesn't automatically stop. The automatic button here can call the local optimizer within this, but clicking start turns on the hammer optimizer. It's called the hammer because it continues hammering away at the same problem. And because it doesn't automatically stop, it also can get outside of a local minimum. And so thus this is considered more of a global optimization tool. All right, doesn't look like it's going to find a much better solution now, so I'm just going to go ahead and stop it. But we can try running this again later after I change one more thing in my system. So as you can see right now, all of these are standard surfaces and the conic constant is 0. But let's say that we wanted to turn one of these into an aspheric surface and optimize the conic constant. We have a tool that can do that for you called the Find Best Asphere in the Optimization tab. So this tool can actually find a significantly higher order aspheric type surfaces, but we're just going to set it to conic right now. So this means that we're not going to change the surface type from standard. All we're going to do is find which standard surface best improves the performance of the system if we allow the conic constant to vary. So this tool steps through surface by surface and turns on this conic constant to a variable one at a time, and then will tell you which surface has resulted in the best merit function. So right now it says the best merit function was on surface 4, but it's testing surface 8, now 10, 11, etc., until it gets to the end. Okay. So you do need to be careful when using this tool because it's using your current merit function. When I first defined my merit function, I set the sampling settings such that we could set it up to optimize for a conic constant. If I wanted this any higher, I would need to increase the sampling density to make sure I could pick up those variations in the surface. Okay, so now I'm going to keep an exit. And you can see now surface 4 has a conic constant. Let's update the spot diagram. Okay, and now let's run a hammer again and see if it gets any better. Okay, it's only been a few seconds and right away we can see it found a better solution. So let's let this run for a few more seconds just to see if the merit function drops down anymore. All right, I'm going to call that good for now, but in reality, you would want to let this run for a few hours and potentially longer depending on how many variables you have in your system. Okay, so now my system is getting closer to being diffraction limited, still not quite there, but here you can see the RMS radius ranges from about 2.1 to, here we have 1.2 and 1.8 microns for the 3 different field points, which all are significantly bigger than the area radius of 0.46 microns. Okay, so let's say that the system is good enough, and now we're ready to lock this down, and we want to tolerance it. Well, there are a few changes that we need to make. One of the biggest ones we can see right away is that we have some surface edges which are not manufacturable. The only way you can get an edge like this is if you're injection molding, but if you wanted to polish the surface, you would not be able to manufacture a sharp edge like this. So what I'm going to do now is make this a flat surface in between the front and back of this middle lens. Okay. So it looks like the clear aperture of the front surface of this middle lens is a little bit smaller than the back surface. So what I need to do is increase this clear aperture, and I also need to drop the mechanical semi-diameter down so it's flat. Okay. So let me pop this out so we can see it when we look in the lens data editor here. So the surfaces in question are surfaces 2 and surfaces 3. Okay, I can see the clear aperture here of surface 3. It's a little bit bigger than that of surface 2, so I'm just going to copy and paste. So now we have a matching clear aperture, but the mechanical semi-diameter is automatically drawn out to the largest semi-diameter of all these surfaces. So I'm going to copy this clear aperture and paste it here and here. Okay, and now you can see the mechanical semi-diameter has been drawn a little bit shorter. Zooming in a little bit further, actually, we can see we have the same problem up at the front surface of this triplet, because the mechanical semi-diameter is a bit larger than the clear semi-diameter. So what I'm going to do is just copy the mechanical semi-diameter value over to the clear semi-diameter. So we end up with a smooth curve. Okay, looks like we have another problem here on this surface. The clear semi-diameter, as it was automatically adjusted for, let's see, surface 9. Here, this is larger than this aperture here. So I'm just going to copy the larger clear semi-diameter over to surface 9. So we get a smooth curve without that hard edge. Okay, now it looks like our system is ready to be locked down and toleranced and then converted to non-sequential mode. So we have a tool in the Tolerance tab here called the Design Lockdown tool. Let's go ahead and save this new system with a different name. And what this Design Lockdown tool does is it applies fixed apertures to all of my lenses. So that means that as they're toleranced and potentially moved around, the semi-diameter won't automatically update. You also can choose to round the thicknesses based on what is manufacturable. Okay, but I'll run this now and then we can look at the changes. So now all of my semi-diameters have fixed apertures. Updating the layout, we shouldn't see anything change. But now we are locked down and ready for tolerancing. So let's look in the tolerancing tab and start with the tolerance wizard. Now I'm going to keep things simple here, and all we're going to look at is an element tolerance, which means moving the front and back surface together. Surface tolerances can be used to tolerance individual surfaces because they aren't necessarily manufactured in the same way. So you could see what happens when a front surface is offset from a back surface or tilted and decentered. You can also tolerance the thickness of the lenses or the radius of curvature, as well as the irregularity of the surface. So what I'm doing here is just a very simplified tolerancing example, and I'm saying that we're going to look at the decentration of, let's just look at one element at a time here. So let's look at a decentration of this last element, which is surfaces 11 and 12. So I'm going to change my tolerancing settings here to start at surface 11, and we'll say it goes down to surface 13, which means we'll be capturing surfaces 11 and 12. Okay, click OK. So I'm not going to go into the details of all of these operands here, but they are fully defined in the help files, and we do have some other tolerancing webinars if you'd like to learn more about that. But the key takeaways here are the minimum and maximum values that have been entered in for the TEDX and TEDY operands. This operand represents a decentration along the x-axis, and this operand represents a decentration along the y-axis. And it is decentering surfaces 11 and 12 together, so they're acting as one element. So these values for the minimum and maximum decentration are away from the nominal, which right now is 0. But this is the default value. I didn't enter these in. Okay. So let's say that I don't actually know what my limit is for these tolerances, but I do know that my spot size can't go above an average of 0.002 millimeters. So what we can do in the tolerancing tab, if we go to the tolerancing analysis, instead of running a sensitivity, we can run an inverse sensitivity analysis. So a sensitivity analysis just evaluates your system performance at these minimum and maximum tolerances. An inverse limit works the other way, and it calculates what these minimum and maximum values should be without surpassing the limit that you've set. So here, let's go to the criterion section. My criterion is the RMS spot radius. If I click check, okay, the merit function it constructs for this criterion is evaluating the RMS spot radius, and here's the value that it spits out right now. So let's say that this value can't go above 2, right? 0.002, because that's worse than what it currently was. And again, this check button displays what the value currently is. Okay. So let's see. In just a moment, I'll talk about the Monte Carlo analysis, but for now, I'll set that to 0. So all we're doing is running an inverse sensitivity analysis. So click on OK. This text viewer gives you the values for each of these different operands. So here you can see how much the criterion changed and what it went to. So it went right to the limit, and it calculates then what the decentration values can be. So if I go back to the tolerance data editor, now these minimum and maximum values have been updated based on the limit that I'd specified. So next we're going to run a Monte Carlo simulation. The inverse sensitivity analysis that I just ran, as well as a forward sensitivity analysis, looks at the contributions from each of these tolerances individually, meaning for this operand, it will decenter the element and then calculate the resulting change in performance. Next, it will decenter the element in the y-axis and calculate the resulting change in performance. In reality, however, there will be some variation of all of the tolerances combined, and this is what a Monte Carlo simulation will calculate for you. So I'm also going to open up some analyses so that we can see the resulting effects. Let's do the ray fan and let's do the spot diagram. Okay, then I'll go back to the tolerance tab and open up the tolerancing analysis. So before the mode was set to inverse limit, and now I'm going to set it to skip sensitivity. All right, that means it's going to skip any of the sensitivity analyses, meaning it's not going to evaluate the individual contributions from each of the operands. So it'll skip this criterion calculation here and jump straight to the Monte Carlo simulation. So I believe the default value for the number of Monte Carlo runs is 20, and make sure you check on overlay Monte Carlo graphics. So that means that it's going to create 20 different files, all with some variation of a decentration in X and Y for the last element. The overlay Monte Carlo graphics means that for each file which is created, it will update the ray fan and the spot diagram with the resulting either aberration or spot diagram. Okay. So you'll notice right away that the ray fan and spot diagram have increased the number of plots, and that's because in a tolerance analysis, you need to trace rays for more field points The decentrations in X and Y require analysis along the X and Y axis, and so that's why you're seeing additional calculations. Okay. So here we can see the spot diagram gets considerably worse for all of these different field points. Same with the ray fan shown here, and it looks like the scale increased to 20 microns as well. Okay, so that was just a quick overview of a Monte Carlo simulation and an inverse tolerance analysis. But let's say that we have all the information that we need and we're ready to convert this file to non-sequential mode for stray light analysis. We've already run the design lockdown tool, which is typically part of the conversion process. So all I need to do is go to the File tab and click on Convert to NSC Group. So as I mentioned, the design lockdown tool has already been run, so I just need to do the critical ray set generator. This traces a set of reference rays, which can then be traced again after the conversion to ensure that the file was successfully converted. Then click OK. All right, and now instead of seeing individual surfaces, I have lens objects, which make up surfaces here 1 and 2. In addition, OpticStudio automatically added in source objects that represent the 3 different field points. And because this had an object plane that was not at infinity, meaning it was a finite distance away, it also could calculate the full field source. And so it automatically added in a source DLL called Lambertian overfill, which is a source object whose parameters are automatically calculated to fill the full field source area. And it added in a bar chart in case we wanted to look at the full field imaging performance. My stop surface is now an annulus surface that's absorbing, so it's behaving as a true limiting aperture would. Then I have a reference object here indicating where the sequential image plane is located. And I have 3 separate field detectors representing the 3 different points where these fields get imaged at the image plane. In addition, similar to the idea behind the Lambertian overfill and bar chart objects here, we also have a larger area color detector covering the full area of my image plane. Okay, so here if you look at this, let's open up a shaded model view. My system looks almost exactly the same as it did in non-sequential. Note that the full field source automatically has its rays turned off, so you'll have to manually turn them on if you'd like to see the effect. The detectors are not set to be absorbing, so we are seeing rays traced all the way through them. But let's set this to have a 50% opacity so we can see the lenses within lenses. All right, so we can see the middle lens here. And now let's harness some of this non-sequential power and show what happens when we trace rays along a path other than the primary intended path. This will result in quite a few ray segments, so I'm going to reduce the number of rays that are drawn in the layout. I'm actually going to turn off the rays that come from the off-axis fields, and let's say we only want to see 5 rays with the on-axis field. Looking in the shaded model, here we can see our 5 rays that get traced down to the image plane over here, but they're all following the intended path. Now when I turn on ray splitting, you'll see all of the rays that bounce around inside of the system. Oh, so I'm seeing this error message here, not enough segments allocated to trace all possible paths, because there are quite a few segments, but we can actually ignore these trace errors in the layout so that the number of rays supported within memory will still be traced. Okay, so there are quite a few, and this is pretty difficult to analyze, but there are a few tricks we can play. In the settings, let's change the color rays to segment number instead of source number. A new ray segment is created each time a ray intersects a surface. So after a ray hits the front surface, it will change color. After it hits the back surface, it will change color, etc., all the way through the system. Now there still are quite a few rays, and there are a lot of rays that miss the detector shown here altogether. So what we can do is use a filter string here to show only rays which hit the detector, the large area detector, which I believe is object 18. Let me double check. Yes, object 18 is the large area detector. Hit 18 and OK. Now all of the rays that are traced pass through the detector right here. There's one other tool that I need to show you, which is up in the Analyze tab here. It's the critical ray tracer. So we hadn't actually validated that our system was converted correctly. When you run this tool, you can use the input file that was created just before I converted to non-sequential. And here you can see a pass-fail marking for all of the rays that were traced in that reference file. And here you can see that all of these rays, for which the target location was determined in sequential mode, they all have the same target landing point in non-sequential mode. And therefore, we know that the file was converted successfully, and thus I can continue with my non-sequential analysis. All right, so that's the end of what I have planned for the demonstration here. We ran through quite a few different OpticStudio tools, but just to summarize, we started with a microscope sample file, and we analyzed the initial performance using the spot diagram, ray fan, and Siedel diagram tools. We also used some full field tools, including image simulation and grid distortion. Then we optimized for the smallest spot size. We started with manual optimization tools called the quick focus tool, the slider, and the visual optimizer. Then we used the optimization wizard to put together a default set of operands in the merit function and added in our own paraxial magnification operand as well. Then we ran the local automatic optimizer and the hammer optimizer. We also used the Find Best A-Sphere tool, and after using that, we saw more of the effect of the hammer optimizer. Then we locked down the design and adjusted the semi-diameters, ran a tolerance analysis. We used the inverse sensitivity tool to calculate the allowable decentration of the last lens here. Then we ran a Monte Carlo simulation to look at the effects of all of the tolerances at once. And then lastly, we converted the file to non-sequential mode. All right, so at this point, I would be happy to take your questions. If you look in the control panel for GoToWebinar, you can see a questions section, and just type your questions there, and you can send them to me, and I will answer them right now. If we don't have time to answer all of your questions during the live Q&A session, don't worry, we are still more than happy to get back to you. You'll just have to do it over email. So you can see the support email address shown on your screen. Please email support@zemax.com, and I'll try to answer your questions via email if I don't get to them right now. All right, so with that, I will take your questions. Okay, so it looks like the first question is, when you use the slider to adjust the parameters, is focus occurring also? So I'm guessing that this is referring to either the quick focus adjustment or paraxial focus adjustment. And the answer is no. The slider and the visual optimizer are only changing the parameters that you see in the editors. There's no additional compensation or adjustment that's done once you manually change them or drag the sliders. Okay, so there's a question about the filter string I used at the very end. It is H18. I was a little unsure where you determined that. Very good catch. I determined that from memory because I've used the filter strings enough that I know which one to use. When you are first using the filter strings, I'd recommend bookmarking the section of the help files that lists all the filter strings, or you could print it out. And so H18 just means hit object 18. And there are a lot of other filter strings that are structured very similarly. Let's see. Okay. We have a question about lens mechanics here. So yes, this webinar is actually part one in a two-part webinar. So this webinar was just focusing on some design, tolerancing, and non-sequential tools in OpticStudio. But next up, Esteban Carbajal will be presenting about how to build the optomechanical components in this same file. So we'll actually be sending him the sequential file that I finished before converting to non-sequential mode. And then in next week's webinar, Esteban will build all of the optomechanical components in LensMechanix. Just so you know, all of the files that I showed in the webinar today, as well as the PowerPoint slides, can be downloaded on our website. All the previous webinars are in a section called OpticStudio Recordings. So everything will be available to you after the webinar as well. All right, well, thank you everyone very much for attending. It looks like we've answered all the questions. If you do have any other questions, you're more than welcome to email us at the address shown on the screen here. It's support@zemax.com.